weird, because when you said it, I pictured you in California. I mean, I know you were at CERN.
Oh, yeah, no, I was at Brookhaven.
Huh. Did you spend any time there?
Yeah, like 9 months on Long Island before going to CERN. Be recorded. No, be recorded. But I liked working at Brookhaven in general. It was good. They're a good group.
They only have a couple Atlas people, right?
No, they have a huge Atlas
really?
group. 40 authors.
Oh.
Yeah.
Interesting.
They were...
I guess I went there and I met with a lot of the Phoenix collaboration people. So I guess I met, like, there's a couple of people who have overlap with the Phoenix.
I see.
But,
Yeah. No, a lot of Susie, a lot of... yeah, it's huge. It's really big. They have a big tier 1 there. So, like, they're like the biggest center in the U.S. for computing for Atlas.
oh, yeah. Yes.
Stuff like that. So.
But I didn't know they had so many local people.
Oh yeah. For a while, a lot of them were conveners, etc. So they were based at CERN. But they really did a good job of sort of integrating themselves into Atlas early enough after the SSC that they could just sort of really blend in and helped build the calorimeter electronics, and that really helped, I think, get them in and established. They were really seen as one of the groups that helped start Atlas, and so
Cool.
politically that was very convenient.
How many postdocs did they have then?
So at the height, I think only like 3 of us, and no students. So
Yeah.
yeah,
Okay.
a lot of staff scientists. Yeah. But I think the postdocs have done pretty well. Like, you probably know Kyle Cranmer.
Yeah.
Yeah, he was a Brookhaven postdoc also. Just before me, and then he left just before I showed up.
Boston's thing about theorists has always been thinking about the 3 to 10 gold numbers very
So did you have an apartment in Brookhaven, or since you were only there? Is it 9 continuous months?
Yeah, yeah. In Sound Beach.
Then again, they sent the
It was like in a house. I was mostly cranky about it because it was really expensive.
Really?
Everything was so expensive there. Like, not close to anything. Right?
Yeah. Except the Hamptons.
Not even really. Still enough. I think it's a Long Island, right? So it's still like another 45 minutes out.
Yeah. Huh.
And there's nothing near the lab itself. It's in the Pine Barrens.
Yeah. I went there for the first time a couple months ago, and I was like, oh, this is not what I imagined at all.
Yeah.
Yeah. We're actually thinking about going back. I'm on the APS committee on the status of women in physics, and we're having our next. We almost always meet at the APS headquarters in DC. But we want to meet with all the APS journal editors, and so we're thinking about having the next meeting. Well, the next meeting is going to be in New York, like at the APS place. But I don't know. It's in March.
Just across from the
Just across the lab. It's in March, and I kind of want to go. It's just if it's like 8 hours, we just sit in a room together for 8 hours. Like she can totally do that.
Yeah.
But I'm also like, is it weird to like just bring a baby to a meeting? I don't know. So I'm not sure.
It's a committee of the status of women.
Yeah. I feel like I should just bring her.
Yeah.
Do you know probably Kathy Prestridge? She's a plasma person a fluids person at Los Alamos. She was the previous chair of the committee, and if it were her, I would totally just do it. But there's a new chair now.
Oh, I see.
I don't know if she'd
Who's
be
the
okay
chair?
with it. Well, it's Ashley De Silva, who is totally cool. But this is like she's just starting the chairship, and I feel like she might feel weird taking a stand about it. I don't know. But I think I'm going to do it.
Why not?
Might as well.
She's a bit of a distraction just because she's so cute.
I know.
That's the only thing.
Oh, she's sleeping. Like, there are lots of people there who are distractions.
Yeah.
I feel like at least one person is a distraction, and at least one person contributes essentially nothing. So like if I go and either of those things are true, no big deal.
Hi.
Hi.
I'm Stephanie.
Welcome you here.
Thank
Carl
you.
Guitar,
Nice to meet you.
the chair. So I was just rushing around this afternoon.
Yeah, no worries.
Like a chicken with a head cut off.
It's nice to meet you.
Nice to meet you.
see. Rye. Is that okay?
Okay, I think it'll be okay.
Okay. Are you going to stay for the whole talk or do you have to rush out to the end? Okay.
We're waiting right now.
Okay.
I think I'll be safe.
Okay. But if I'm not here, can you do this?
I'd like to borrow that book from
Okay.
It's just looking
How
for
long
the
do we usually wait, Carlton? This clock seems different than this week.
Don't forget to introduce the wrong revision.
New assistant professor?
Both.
The new assistant professor.
Yeah.
The hires are getting younger and younger.
The newest physicist in the past.
I don't know. She's making lots of noises. She might be like a linguist or something.
Don't let her be a lawyer.
We're all
What's wrong with lawyers here? Yeah.
My husband's a lawyer.
Sweet. Sorry.
Okay, everyone is silent. I think we've developed a group of people. Okay, so I would like to introduce our visitor, Colloquium speaker today, and HEAP speaker tomorrow. So if you like what you hear, then please come to the HEAP seminar tomorrow at 11. This is Stephanie Majewski from the University of Oregon. Stephanie got her PhD from Stanford in 2007, working on the bar, and then did a postdoc at Brookhaven, but she switched to Atlas, so she was mostly at CERN during that time. And she's been at Oregon since 2012, and she's going to tell us about searching for supersymmetry. So let's welcome Stephanie.
Any other introductions?
Oh, let's clap for Stephanie. And this is Cora, who we hope will be good throughout the talk.
Thanks very much for inviting me. Yeah, so today I'm going to be talking about Atlas and the search for supersymmetry there. So let's see. All right, so I'll start out with the Large Hadron Collider, which hopefully most of you have heard of. And so we collide protons at the LHC, and at a center of mass energy, I put an arrow to 14 TeV. So the design energy is 14 TeV. We've only made it up to 13 TeV center of mass energy so far. Oh, yeah. Makes it a little easier to see. Thanks. No, that's wonderful. The circumference of the ring is about 16.5 miles, which is here. You can see some landmarks here. This is Lac Léman near Geneva. Geneva itself is over here. This is the Geneva airport. This triangle indicates the main CERN site. And over here are the Jura, the foothills, just outside of Geneva. And actually, the ring itself crosses over the border from Switzerland into France as well. So there are the two sort of large multi-purpose experiments at the LHC, Atlas, which is the one I'm working on and the one I'll be talking about today for the most part, and CMS, the compact muon solenoid, which is all the way on the other side of the ring. The nice part for us is that we're really just across the road from the main CERN site, so it doesn't take us very long. To get to CMS, you have to drive through a lot of fields and rural areas and sometimes get hit by, run into cows in the road, this sort of thing. So we have a little bit of an advantage. The other two experiments are ELISE, which specializes in heavy ion physics, and LHCb, which specializes in B physics. So, like I said, today I'll be mostly focusing on Atlas, but there are a lot of interesting results coming out of all of the experiments. This is a picture inside the tunnel, the LHC tunnel. These are these large superconducting dipole magnets here, about 1,200 of them around the ring. They are cooled to 1.9 Kelvin, and so this is really a quite impressive machine all the way around. And you can just imagine the engineering challenges, getting this machine commissioned, upping the energy at various stages, and keeping it running smoothly to deliver collisions to the experiments. So I'll just give you a little bit of a history of sort of the startup of the LHC. The first collisions were actually only at 900 GeV center of mass energy back in 2009. About 6 months later, the LHC was able to bring that center of mass energy up to 70 eV, and at the end of March 2010. We finally got 5 inverse femtobarns delivered October 2011, and then increased the center of mass energy again to 8 TeV in 2012. And got 25 inverse femtobarns delivered at the end of 2012. And actually, these are most of the results that I'll be talking about today and tomorrow in the seminar is based on that data set. We are running again, and I'll explain a little bit more about that. We increased the center of mass energy to 13 TeV just last year after a 2-year shutdown to do some repairs and upgrade the machine. So that happened in 2015, and we are expecting about 100 inverse femtobarns over the next 5 years in run 2. So in case you're not super familiar with this unit, inverse femtobarns, 1 inverse femtobarn is about 100 trillion collisions, roughly. And here is a picture from the first LHC collisions at 7 TeV in the Atlas control room. So this March 30th, 2010, this is the group of us working on the liquid argon calorimeter and its commissioning back then. It was a really fun time to be there.
So each one of those collisions gives you some data?
Yeah, that's right.
But there are a lot of collisions that take place that you don't see.
That's right. So, in fact, we can only record a certain number of them. In principle, we could, if we had the best electronics ever, we could record them all and write them all to tape, but we're actually financially limited for the most part. We have a 3-stage trigger system. So the first stage actually runs at about 100 megahertz, and then we have to sort of wean that down to something that we can write to disk, which is about a few hundred hertz. And that's about how much we can store to tape, actually. So we have to make the trigger system, which I won't really talk about too much in this talk, is an amazingly complicated system, and we rely heavily on it to pick out the very interesting events. That's exactly right, yeah.
Another stupid question, is that actually tape, or what do you use?
Yeah, so we do have a mix of disk and tape, actually. I mean, just because it's cheap. So, yeah, exactly. Let me see if we can speed this along. There we go. Okay, so I would like to motivate the physics that we're doing and sort of why we're doing it. So I'll start out with the standard model of particle physics. So this is the theory that describes all of the particles that we know about so far. The fermions, which are spin 1/2 particles, half integer spin particles such as quarks, electrons, muons, tau leptons, neutrinos. These are all in the fermion category, and bosons. These bosons are the force carriers, the photon, light, that we're very familiar with, the gluon that holds together protons and neutrons and other is the carrier of the strong force, and the W and Z, which are the weak bosons. So these force carriers are integer spin bosons. The standard model so far has been hugely successful, and so this is a graph of the cross-section here versus the center of mass energy when you collide 2 electrons together and get hadrons. So you get groups of mesons and baryons out of this. And so you can see the curve here is the standard model prediction, and the points here all represent different measurements, actually at different colliders, different continents, different time periods, and you can see that they all match the standard model prediction really beautifully well. And this peak here is the Z boson resonance. So here is just a list of all of the experiments whose data, or colliders whose data are shown here. For example, SLC was at SLAC. PEP2 was a storage ring, also at SLAC, where I did my thesis experiment. LEP at CERN in the same tunnel as the LHC, but an electron-positron collider before. So all of these experiments give us these beautiful agreement with the standard model. However, hopefully you noticed here that I was missing a very famous boson from my list, and in particular, the Higgs boson. So this boson is extremely famous in the past few years. It started out actually in December 2011, so this was just at the end of the 7 TeV run. We had just collected about 5 inverse femtobarns of data at that point, and we started to see hints that maybe there was a sign that the Higgs boson was there. half a year later, we actually confirmed that. And so the signature for the Higgs boson looks something like this. This is one of the golden modes for its discovery. The Higgs can decay into two Z bosons, each of which can decay into an electron-positron pair, or, for example, a muon-anti-muon. And so a 4-lepton event like this, where you have 2 electrons and 2 muons in your detector, who, when you reconstruct them, their invariant mass adds up to the Higgs boson, is sort of the smoking gun for its discovery. So this is kind of a cartoon of a Higgs event. I will show you then the reconstructed events here. So this plot is going to be events in 5 GeV bins, and this is exactly the mass of those 4 leptons that I was talking about. So if we can reconstruct the invariant mass of those 4 leptons, we can make a histogram of the distribution here. And what I'm going to show you is a time lapse, actually, and as the data sort of increases, it will be moving forward in time. The points will be the data, and we have some colored histogram filled in here for the background, mostly the red and purple. The dominant is just ZZ production here. So here's the little simulation, which you can see of just showing the integrated data over time. And you can see that this peak starts to show up here quite a bit above the background. And in fact, the blue here, the light blue, shows a standard model Higgs with a mass of 125 GeV, and this is the standard model prediction for its strength at that mass. So you can see this really beautiful plot and this very large peak in the data above the background. So this was one of the channels in which the Higgs was discovered. And so about a half a year later, July 4th, actually, 2012, we called it Higgs Dependence Day when we were at CERN. We all gathered in the auditorium and various satellite auditoriums because, in fact, you had to camp out overnight to get into this main auditorium, and all of the CERN summer students definitely did that. And so for the main announcement of the Higgs discovery. So that picture is shown here with Peter Higgs present. So the Higgs discovery is really the last piece of the standard model. It fits in beautifully. It gives us the very last piece in this theory that is working extremely well. We got recognized for it in a variety of different ways. Fabiola Giannotti, who is at the time was the spokesperson of Atlas, she made the cover of Time magazine as one of the people of the year. She is now actually the Director General of CERN overall. And Peter Higgs and Francois Englert won the Nobel Prize, in fact, as well, in 2013. And the prize motivation was for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle that you know as the Higgs boson. And so this is actually one of my favorite pictures, is Peter Higgs actually holding one of these stuffed particles from the particle zoo. It's kind of funny that someone convinced him to pose for that. Anyway, so after all of this, you can kind of say, okay, so the standard model is extremely successful. It's held up to many of these precision tests. But even with this Higgs boson discovery, we actually still have quite a few unresolved questions to answer. And so this is going to be the focus of my talk today, is to talk about how we're looking for some of those additional answers and what those additional questions are. So I'll start back with the quarks. So these are these spin 1/2 particles, fundamental. They make up all of the matter that we see as far as the proton and neutron contain the up and the down quark here. You have more exotic quarks like the strange quark, which is also very light. You have the charm quark, which is 1.5 GeV. It's around the mass of the proton. You have the bottom quark, which is around 5 times the mass of the proton. And then you have the top quark, which was discovered about 20 years ago and is actually 175 times the mass of the proton. And we have no idea why these quark masses are so different from each other. This is a main, really big unanswered question still from the standard model.
Why do we need them?
Why do we need them?
Yeah, we need the little ones there to make protons.
Right. Right. That's another question, in fact. I mean, maybe the astro people in the room can talk about also, expansion of the universe, etc., right, and why we need these. So, yeah. And so the other thing, another sort of unanswered question, has to do with sort of the scales of the physics that we know about. You can start out with neutrinos that may be around an electron volt or lighter. You can talk about, the core of the sun, an electron, which is around an MeV. The scale of the strong force compared to the atomic force, this is about 10 to the minus 15, this is 10 to the minus 10. This is the scale of the proton, of the muon, the pion, etc. The weak force, in fact, is more like 10 to the minus 18 in scale, and this is where the top quark hangs out. The Z, the W, the Higgs, sort of the electroweak scale is set up here, and these are actually the energies where the LHC can access things. And then we have a really big desert in between these scales that we know about and any other scale like the grand unification scale or the Planck scale up at 10 to the 19 GeV. And so this is actually one of still the big unanswered questions. Is there new physics in between sort of this scale and the Planck or Gut scale? And that's one of the really interesting questions that we're trying to answer. So I'll try to motivate that a little bit more by coming back to the Higgs. So the Higgs mass, you can think of it as made up of two components. One, a so-called bare Higgs mass, and the second part, which is the radiative corrections to this. And you can think about these radiative corrections as being the Higgs mass coupling to the other particles that we know about. In particular, coupling to the top quark, which is so heavy. The Higgs likes to couple to the heavier particles. And here as well, coupling to the Higgs itself, to the W and Z bosons. So in fact, these radiative corrections here quadratically diverge. And so we need to introduce some sort of cutoff scale to protect these integrals, basically, from blowing up and make the theory solvent. So if you start to just work out the math a little bit, you can say, okay, we know the Higgs mass, the observed Higgs mass is 125 GeV. We have the bare Higgs mass, which we don't know what it is, and we've introduced some cutoff scale, this lambda here. Now, if there's no new physics between the electroweak scale and the Gut scale, then lambda has to be something like 10 to the 16 or 10 to the 19 GeV. So if you think about what is needed then, that means these two numbers have to have a huge cancellation between them to get down to a Higgs mass that's really light, that's 125 GeV. So this is called the hierarchy problem, and if lambda is really this high, an unimaginable amount of fine-tuning is needed to keep the Higgs mass as light as we've observed. So this is one of the real unanswered questions that is hanging out there in the standard model that we need to understand. So the question then is, can we introduce a new scale with new physics, perhaps at 1 TeV or so, to protect the Higgs mass and minimize this fine-tuning? And so one of the ways that we can do this is to introduce a theory called supersymmetry. The other thing that we can do, of course, many of you recognize this as the bullet cluster, as a signature for dark matter, and it's part of the evidence that's speaking to it being a particle. And the other big question that we have is, okay, dark matter is, let's say, 24% or so. How does this fit into the picture? If dark matter is a particle, how does it fit into our standard model of particle physics? We have this beautiful theory that describes all of the known particles extremely well, and we have no idea how dark matter really fits in. So here's back to the standard model, and one of the ways that we can start to explain this is to introduce new physics, these new additional models, perhaps at the TeV scale, that start to answer some of these questions. Supersymmetry is a really nice stand-in for a representation of all the beyond the standard model physics ideas that we have, and it's a really compelling one. In particular, it works by introducing a symmetry between fermions and bosons here. So here are all of our known particles, and the idea is that in supersymmetry, they all have a heavy partner. And in fact, the heavy partner to the fermions are all bosons, and the heavy partners to the bosons are all fermions. So this symmetry is one of the ways that we can start to answer some of these questions. And if these heavy particles exist, we can show that perhaps supersymmetry is an explanation for this physics beyond the standard model and maybe some of these answers to these questions. And the way this works, in fact, is that quite naturally, you remember these radiative corrections to the Higgs mass with these top loops in the Feynman diagrams. In supersymmetry, every quark that we know about, for example, the top quark has a partner called the stop. In this case, you just throw an S in front. And these two diagrams actually fairly naturally cancel and give you a natural correction to the Higgs mass in these radiative corrections. So they solve this divergence in this hierarchy problem. problem if supersymmetry exists. Okay, and then finally, in supersymmetry, you also are given, especially in our parity-conserving models, a dark matter candidate in the sense of a neutralino or a gravitino, which is the partner to the graviton. And these would provide an excellent dark matter candidate. They're weakly interacting, they're stable, and they could easily be the dark matter candidate that we see from cosmology.
How are they better candidates than the neutrino and the graviton?
Right, so there's a lot of evidence actually that the neutrinos cannot, the neutrinos are warm, and as far as what we know about dark matter, it has to be cold. So in fact, that speaks to something like a neutralino, for example, that's extremely weakly interacting. So neutrinos themselves can't be the dark matter solution, unless you are talking about potentially a sterile neutrino model, something like this, but even that I think is a little bit on the edge. Okay, so here's a quick recap then. So we've said the standard model is successful, but it leaves us with unanswered questions. And so the idea is maybe we can answer some of these with supersymmetry. So now what I would like to discuss is how we are searching for these at the LHC, how we are searching for these supersymmetry signals. So let's go back then to a picture of a proton. So this is sort of the medium for our experiments. It all comes back to the proton. This is a very naive picture of a proton where you have 3 valence quarks, 2 ups and a down quark. They're bound together by gluons inside the proton. Perhaps a slightly better picture of a proton is these 3 valence quarks, but then a seething sea of these gluons that are producing up-up bar, strange bar, other quark-antiquark pairs in this sea inside the proton. And so perhaps even this is a better picture of this. So as far as an instrument for doing our experiments, the proton is an extremely messy place. This is not an electron-positron collider where you are colliding point particles. Instead, you're colliding bags of stuff, basically. The other thing is that you need to know if you're building sort of a mental model of what's happening here is that each proton is accelerated from its rest mass of about 1 GeV to an energy of 6.5 TeV in the collider. So actually they're really compressed, and so one analogy is thinking of this as like blueberry pancakes that are colliding. I mean really you just want to think of a huge mess here. So here's a little cartoon where each of the dots inside the proton could be a valence quark, one of these C quarks or antiquarks, or a gluon inside the proton. So when the 2 protons collide, we're actually not sure which constituents of the proton are going to collide with each other. At the LHC energies, it's most often gluons, but you can get quark-antiquark interactions, you can get quark-quark, you can get quark-gluon interactions. So here's a little cartoon of this, and what happens most often is that you get 2 gluons colliding with each other, and they just produce 2 gluons again. Kind of boring. These are these boring events that we discussed earlier that are actually not extremely exciting because they're really just they produce 2 jets or collimated streams of particles coming out of our collision. So the thing to note is that the outgoing quarks or gluons only carry a fraction of the proton momentum. And in fact, we don't know what that fraction is in the longitudinal direction. All we know is that the initial state of the collision had no net transverse momentum. So we know that in the final state, there can also be no net transverse momentum. And that's what we need to use to determine if there are any missing particles that came out of our collision. So here's what that cartoon event now looks like in the detector, and this is an actual event in ATLAS. You can see these 2 big splashes of collimated particles in the detector, their interactions in the detector, and you can see these 2 peaks here. This is eta phi, this is the coordinate system. If you unwrap the detector, the cylinder detector, into a sheet, you see these 2 spikes corresponding to the energies of these 2 jets that came out of this collision. And in this particular collision, they have transverse momentum of about 1 TeV per jet. So, and this is just a side view of that same event. So the instrument that we use then to measure these collisions is the ATLAS detector. And this thing is quite large. It's about 5 stories tall. It's about 7,000 tons, so it weighs as much as the Eiffel Tower. If you wrap this thing, though, in saran wrap and stuck it in the water, it would float. In fact, there's actually a lot of empty space in there. The liquid argon calorimeter itself, which I'll talk about in a second, has something like 180,000 channels. This is an extremely complicated, detailed detector that we need to use to see these events, in fact. And so you can see people here that are extremely tiny compared to the scale of this detector. And you can tell Atlas from CMS because it's the one with these big muon wheels at the end, which, remember, that's the one that looks like a Tootsie Roll. Got it. CMS doesn't have those big wheels on either side. Okay, so going from sort of the inner part of the detector outward, it's actually built up like an onion. So each part of the detector has different functionality, and it's built out in layers. So this inner part of the detector is designed to, it's a tracking chamber, basically. It's silicon. There's a pixel detector and a silicon strip detector in there. They're bathed in a solenoid magnetic field that bends the charged particles so we can measure their momenta. Outside of that, we have the calorimeters. So there's a calorimeter that's where the active medium is liquid argon. There's also a tile calorimeter. This is the electromagnetic calorimeter designed to detect electrons, photons, etc. The tile calorimeter helps out with jet reconstruction. And so then outside of that, we have the particles that escape all of the rest of this are basically muons and neutrinos. The neutrinos go all the way out and we never see them, but the muons interact in these outer tracking chambers out here where there's an additional toroidal magnetic field to again bend the muon and get a good measurement of its momentum out in this part of the detector. So now if we look at this picture again, this is this exact same event. This green part here is the electromagnetic calorimeter, and the red part here is the hadronic calorimeter. And so you can see these are the parts of the detector that we use to actually measure jets in our detector. And this is extremely important for looking for things like supersymmetry. So if we go back to this idea of, okay, so we know that most of the time gluons collide and produce gluons again. Another thing that can happen, though, is that we can collide these two gluons that are inside the proton and get a top-anti-top pair out, so a pair of top quarks, basically, out of our collision. And what this might look like in the detector, this is sort of our cartoon of the decay. So here's your top and anti-top. Each one of them decays to a bottom quark and a W boson on both sides, but then the W boson can actually decay a couple different ways. It can decay to a quark anti-quark of a different flavor, or it can decay to an electron, muon, or tau with a neutrino. And so we have these top quarks that we can observe in our detector, and in fact, the LHC is really considered a top factory because we're able to produce so many of these events. So I wanted to tell you a little bit about how we actually observe these events. And so if you think about the number of events observed, it has basically three components. It has the integrated luminosity, the efficiency, and the cross-section for that process. So the integrated luminosity, it's what's delivered by the LHC and then recorded by Atlas. So we need a functioning detector built into this. So if the LHC delivers everything and we don't have a well-running detector, we won't record much of it and we can't see many events, right? So it's pretty straightforward there. The efficiency is optimized by experimentalists, and this is what I do. Actually, most of my job is to optimize this efficiency, looking for these signals of new physics and seeing how we can be very efficient for producing them. For detecting them compared to backgrounds. And finally, the cross-section for this process. So this is calculated by theorists and measured by experimentalists. So if we look at the cross-section for producing TT bar events, so top-anti-top pair production, we can see that at a center of mass energy at 7 or 8 TeV, it's about 200 picobarns cross-section according to these measurements. And actually, the data and the theory calculation are in good agreement with each other. So if we just go through a little exercise here and say, okay, let's say we have 1 inverse femtobarn of data, which is equal to 1,000 inverse picobarns of data. That means that if we have an efficiency of 10% for measuring these TT bar events, and the cross-section is about 200 picobarns, we end up with 20,000 events. Okay, so what happens now if we're looking for supersymmetry? Well, let's say we're looking for a gluino. This is the partner to the gluon. And this is a potential supersymmetry particle that could be produced in one of these proton-proton collisions. Let's say we produce a pair of them, each at 500 GeV in mass. The cross-section for that is about 2 picobarns, so a factor of 100 less than the TT bar cross-section. And in fact, then, we do the same exercise in the same data set, we get about 200 events of these gluino pairs. So you can already see that, and that's assuming we have the same efficiency for detecting both kinds of events. So you already see we have a challenge. It's not insurmountable, but we have a bit of a challenge. So we are looking for these gluino events, but we are also looking for the stop. So this stop, you can see that cross-section, if you had a center of mass energy of 7 TeV as well, a 500 GeV stop actually has a much lower cross-section for producing it than the gluinos. And the cross-section is only about 0.05 picobarns. So now instead of 200 events, we actually only have 5 events in 1 inverse femtobarn of data. So you can see sort of what we're up against as far as, you know, signal to background just being produced in the collider. So it really is a needle in a haystack. And so we had 1.8 trillion events in 2011 in 5 inverse femtobarns. We got about 4 times this in 2012. And that in itself was 1,900 terabytes of data. So this is a lot of data that we're recording. So here's the actual signature for detecting one of these gluino decays. So the 2 gluinos are produced in your collision, just like the gluon-gluon, but with this particular cross-section, this 2 picobarn cross-section. And each gluino might decay to a regular standard model particle, couple quarks here and here, and also to this funny-looking thing called a neutralino, which is our dark matter candidate. So this is at chi 01. What this looks like in our detector is jet, 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 and then some missing energy because the neutralinos pass right through our detector undetected. And so we can determine the missing energy by adding up the 4 vectors of all of the jets and taking the opposite of that to get your missing energy. So these are the particles that escaped. And we also can create a quantity called an effective mass, where we just add up the scalar sums of the transverse momenta of the jets plus the missing energy. And this is a representation of the mass of the original gluino-gluino system. So these are 2 handles for looking for these gluino decays. So now I'm going to show you a plot of the data, but just to introduce you to the axes, this is another histogram with 100 GeV bins this time versus this M effective variable, this effective mass. And this is with 1 inverse femtobarn of data. And so you can see then the data here is the points. The colored histograms are the backgrounds. You can see that they're backgrounds from QCD multi-jet events. So that's like those gluon-gluon to gluon-gluon events, but then they might split and give you multiple jets. W plus jets events is the light blue. Z plus jets events is the dark blue. And then TT bar is there in the light green. And this dashed histogram is stacked on top, and that's what you would expect the data to look like if there was a signal for these gluinos. Unfortunately, in this case, we didn't see it in 1 inverse femtobarn at this mass. And this is just the ratio then of the data to the background estimate. So we can then optimize as well for higher mass SUSY and make an additional plot. And this in particular was a very highly cited paper out of Atlas in the first inverse femtobarn of data. So basically, as soon as we had the cross-section to look for these gluino events, we started to, and in the first inverse femtobarn of data, we could say, okay, we don't see gluinos in certain mass reach. This SUSY search is not going to be as easy as we thought it was going to be. But we did see some events with very high effective mass that are very pretty. Here's an event in the detector. You have missing energy. You have these beautiful jets. Here's again that Lego plot with some very high PT jets here with missing energy of 460 GeV, these jet PTs of 500 GeV or so, and an effective mass of 1.8 TeV. So this was a very high energy, high effective mass something that was produced, but it just very well may have been TT bar or Z plus jets or W plus jets that coincidentally looked enough like a gluino event. So Atlas and CMS have been really doing these types of searches. I gave you sort of a taste of one of the searches, but they've been doing these searches across the board. And this was updated in July 2015. And the green bars show you the reach of all of these searches. And you can see here where the 1 is marked, this is a log scale. This is the mass scale of these searches. And these are all different types of searches that we could do with with the people and the detector, etc. And so here's the TeV scale is about here. And you can see that many of these searches are approaching that TeV scale. Similarly, CMS has a similar type of plot, and here's the 1 TeV line about there, and you can see that they're approaching it in many of the searches. So we are accessing the TeV scale, but we haven't seen a sign of supersymmetry just yet. So the question is now, should we give up on supersymmetry? And my answer to you is no, not yet. We're not quite done yet. Even if most of these squarks and light flavor squarks and gluinos are heavy, maybe this stop squark could still be light. And if you remember the diagram, the important diagram to cancel in the Higgs mass divergence is the top loop in that diagram. And so what you really need is a relatively light stop to try to cancel that out. And that's really the main contribution to the fine-tuning, so perhaps the stop could still be light. So if you remember this, this little thing, the top quark itself, right, this is the main contribution to that diagram. So the question is, could the stop be the lightest squark? So as I mentioned here, the stop is actually special, and this is a picture that was taken at Fermilab, in fact. And yes, they got in trouble for this, I believe. The Fermilab police were not very happy about that. But this is this diagram that we were wanting to cancel, this radiative correction to the Higgs mass. Okay. So in 2011, even before the Higgs was discovered, a bunch of theorists, experimentalists got together, and this transparency is from Nima Arkani Hamed, who kind of summarized it in one very succinct way. This is the sparticle mass on the y-axis of this very nicely detailed plot. And this is showing you a possible SUSY spectrum after that one inverse femtobarn search for gluinos didn't show any smoking gun sign of SUSY. And so in that case, we could just make the gluino a little bit heavier, a little bit just out of reach. Maybe then you can look for the stop. Maybe it's around 400, 500, 600 GeV. And you have the Higgs at 120 or 125, as it turned out to be. So this is how we then actually look for these stop decays. And what we're looking for is direct stop production. And the really nice thing about direct stop production is that you can kind of ignore all of the other masses of those SUSY particles that we talked about. And you can do this with the gluino decays as well to a lesser extent. But this is really nice in that you can look for these stops just produced directly. And you can calculate this cross-section, as I mentioned earlier, directly. So each stop will decay into potentially a top quark and a neutralino, again, our dark matter candidate. And then each top, if we look at the all-hadronic channel, will decay into a bottom quark and a W that decays hadronically. So what this looks like in our detector is 6 jets, 2 of which are B jets, and some missing transverse momentum from the neutralinos. So the really nice thing about looking for stops is that we can reconstruct these hadronic tops. And this is a plot of this from Atlas. This is the invariant mass of 3 of the jets that happen to be closest together in eta phi space in the detector. And we can plot their invariant mass, and you can see that actually it agrees very well in a control region with the TT bar background. So this is sort of a sign that, okay, this is looking quite good. We're able to reconstruct top quarks, give a very nice, clean hadronic top mass peak. And it looks quite lovely with very few other backgrounds. And this was only with about 5 inverse femtobarns in 2011, so we certainly have a lot more data now. So the other piece of this, of course, is the missing transverse momentum from the neutralinos, which again, now we have 6 jets to deal with, and we have to measure them precisely so that we can accurately measure our missing transverse momentum. And that's actually the biggest trick that we have. I mean, our jet reconstruction performance is actually quite excellent, and it's because of that that we're able to do these SUSY searches with such good results. So you can see here then, the main discriminator in this analysis is looking for events with high missing transverse momentum as well as 2 hadronic top quarks. So we can see here then these are going to be 50 GeV bins, and this is 20 inverse femtobarns of 8 TeV data now. And so again, we have the data are going to be the points, and we have a variety of backgrounds, including the TT bar in light green, W and Z in blue, and the signal for a 600 GeV stop is in pink. So this is what this looks like. You can see a histogram here with the data points overlaid. You can see it's a very tight signal region, and unfortunately the data doesn't follow this curve, which is what we would expect if there was a signal for stop in these events. So we've actually done this not only in this channel, but actually in other channels as well. And we can interpret, at least in this analysis, we've done this in many different signal regions. We can interpret this now in terms of basically a simplified model for looking for these stop decays, where we can just plot this. Since we're looking for direct stop production, you can put the stop mass on the x-axis, the neutralino mass on the y-axis, and we can scan a bunch of different models and see if we had sensitivity to those models. Since we didn't see a signal, we could say whether or not those models are excluded. And so we can do this, well, the assumption here is that it's 100% branching fraction to top neutralino. And so you can see here then, this is the region that we are able to exclude with this analysis with that data set, the 20 inverse femtobarns of 8 TeV data. And everything underneath this thick red curve is the excluded region. For those of you who might know a little bit more about these plots, I can tell you that this blue dashed curve is the expected limit here at 95% confidence level, and then the red here is the observed, and these are the error bands. So this is basically the excluded region that we've observed for searching for these stop events. This small dashed line down here is from the 7 TeV analysis back in 2011. Oh, yeah.
You were mentioning earlier that the neutralino is a candidate for the dark matter.
Right.
Are you also putting constraints on? I mean, you're not mentioning that. You're only mentioning the stop matter. Is that just because you're
right?
On that,
you can interpret this as given a particular stop mass, we can. If the stop decays to top neutralino, then we can exclude neutralinos in that region. But it's not a blanket statement on a neutralino exclusion at all, in fact. I also wanted to mention, actually, that these searches, since they're very simple and we're really just looking for some sort of top partner that might decay to a top and a dark matter candidate, in fact, we are pretty agnostic to the model. We show our results in terms of SUSY models, but in fact, little Higgs models, vector-like quarks, etc., can all be interpreted in terms of these results, and we provide all of the data as far as HEP data is what it's called, to theorists who can then check their model and see if their top partner model is excluded by our search. So then we can now, this is sort of the current state of things after run 1 of the LHC, so after the 2012 data. You can see that this is quite busy at this point. We have a lot of different analyses here. This yellow band here is the excluded region that I showed you, and that's the all-hadronic channel now combined with the one-lepton channel, so where the top, just one of the W's from the top decays to an electron or a muon instead of all-hadronically. So those two, since they're orthogonal analyses, can be combined. I'll talk a little bit more about those searches in detail tomorrow as well. And so that's this region here. You can see the orange here is a different set of analyses that are actually complementary in this region, so also exclude models in this region. In fact, then, there's a bunch of different models, like let's say that the stop is actually much lighter. What if it's even lighter than the top mass? That's what's down here, and you can see a variety of different ways it could possibly decay in that case. And this little triangle down here is what would happen if the stop was nearly degenerate with the top. And so I'll talk a little bit more about one of these analyses tomorrow that was used to exclude this region. Okay. So I wanted to just, wrap up with the thought that the stop is actually quite special. And so since it has this the top quark has this intimate connection with the Higgs mass, we can actually use the Higgs results to give us maybe a bit more of a hint about where the stop might be. So that's what these plots are from Steve Martin at NIU, and this is in the minimal supersymmetric standard model. These are showing the heavier stop mass. What I neglected to mention before is there are actually two stop masses, versus the lighter stop mass. You can really just look at it along this axis, and then the Higgs mass, and what you want to look at is the 125 GeV line here. So this is this black line here, and you can see that these two plots are showing different supersymmetry parameters, values for tan beta in SUSY. And so you can see here that there's some range here that maybe goes up to about 600 GeV, but if you tweak this little parameter, the black line actually makes the heavier stop mass go all the way up, and that the lighter stop mass could go all the way up to maybe even 1500 GeV. So our work is not yet done as far as these searches. And the stop, if you remember from the plot, the stop cross-section drops actually quite quickly as a function of the stop mass. So it gets harder and harder as we're searching for heavier and heavier stops to produce them with a fixed center of mass energy at the LHC. Okay, so I will sort of wrap up here. I really like this picture because it shows just this wonderful contrast between these very slick, nice, modern computer blades and someone looking at a CRT monitor in the middle of it all. And so Atlas and CMS are now eagerly awaiting the start of the 2016 run. And so tomorrow in my seminar, I will go into a little bit more of an outlook about the 2016 run and our prospects for finding stop. I can just tell you that it's going to be a very exciting year. As far as sensitivity, this is probably the biggest jump that we're going to have for a while. We're expecting maybe 20 to 30 inverse femtobarns this year. Last year, we only got about 4. So this year, we're super excited to look for, to really expand our reach to higher stop masses. So we really hope that SUSY is just around the corner and that these theorists were just a factor of 2 off a little bit and that 400 GeV stop is actually maybe just at 800 and we can find it this year. So, and I'd like to conclude with a picture of the team from Oregon. So we have 3 graduate students working on stop searches, Ian, Johan, and Max, and a postdoc, Walter, and that's it for today. Thanks. And I'm happy to take questions, so yes, please.
So is it possible that the other supersymmetric Higgs boson are lost in this signal that cannot be recorded?
That's something that we worry about quite a lot, in fact, is what are all the possible signals and how do we make sure to record them all to tape? And so there's a couple things that are possible. It's possible that it's there in our data now and it's just swamped by background and we can't distinguish it from background just yet. And then maybe we just need a lot more data, a lot more precise measurements to do it. We really hope that we've designed our trigger system in such a way that we worked very hard to try not to let that happen. Could it slip through the cracks? In principle, yes, but we have Atlas and CMS, so there's sort of a safety net there in that sense. And we actually each push each other to do better in all of the data analyses, but also in our trigger systems, and sort of keep an eye on. And we're actually doing upgrades to the trigger electronics, both in 2018 and then about a decade from now as well. And we're both sort of pushing each other to really make sure our trigger systems keep up with the pilot conditions of the LHC and all of the mess that we have to sift through, basically, to find the physics. So I hope that answers it, but yeah. Yes?
Do you make better progress by upgrading the energy or upgrading the timing of your...
Yeah.
Just finding more events?
Yeah, so the luminosity is important and also the center of mass energy. So there's sort of a hardware limit to the design of the machine as in both of those categories, in fact. 14 TeV is the design energy, but because of some magnet issues, basically we're only able to get to 13 TeV right now. And in fact, so the magnets in the machine, even though they're superconducting dipoles, they do have hysteresis and they basically lost their training. I'm not really joking about that. So when they were lowered in, they were trained all on the surface to be able to get up to the currents that would provide 14 TeV. And when they were lowered into the pit, they actually can't get there anymore. And it's a series of magnets that they know about. So it would take actually something like 1,000 quenches or retrainings of these magnets to get them all the way up to design energy. Now they're certainly thinking about this problem, and there are a lot of clever people thinking about if there's a way around it or not. But that's certainly the limitation on the center of mass energy side. Besides that, we'd need different magnets or a bigger machine, basically. The luminosity front as well, there's thoughts about going to a high luminosity LHC. That's the potential machine that's at least a decade away, though. It would require some upgrades. You'd want to upgrade the interaction points to make it a crab-kissing interaction point, perhaps, to achieve higher luminosity there. So there are some thoughts about increasing the luminosity of the machine as well. But at some... With the same beam current, exactly. So those are the options on the table right now. What we really need actually is better superconductor technology so that we can actually bend the beams. So the hard part is bending the beams, in fact, at these high currents, at these high energies. And so if we have better superconductors, we can make magnets in a smaller ring, in the ring that we have, that can accelerate the protons higher. Basically bend them is the difficult part. So, yeah.
So, on the subject of luminosity, so is it high enough now that you often get multiple collisions?
Yes. So, in fact, I didn't even talk about that at all. So, I mentioned that it was messy, but we also get multiple interactions per crossing. And in fact, last year we were getting something like 20 on average per crossing, which is just crazy. How do you sift through all of that? Exactly. So we do a lot of different things, actually. This is where jet reconstruction actually is sort of the unsung hero of all of this. It's sort of underneath all of these SUSY searches, but reconstructing these jets, we use the charge tracks a lot of times in the jets to identify which jet came from the hard scatter and which one came from a different vertex, one of these secondary vertices, additional vertices due to pileup. And so basically we can use that information to also help subtract out energy that's due to pileup in the particular jets and do some corrections to our jets so that we're just looking at the stuff from the hard scatter. It's pretty easy when you have like a zeta mu event where you can identify the muons as both coming from the same primary vertex. That's the hard scatter. That's your real collision that you cared about. But it's a little trickier when you have multiple jet events. You need a high PT jet to say this is the real hard scatter, and then you assign everything else to that and throw out the other jets. Don't count that in your Messini T. Yeah.
Are there any SUSY signatures where if you saw one event of it, you would know you had it?
There are some very clean signal regions. So the one that I showed you, actually, we did have a signal region where if we saw 3 events, you would know it. There are some searches. I think maybe the best example are these sort of disappearing track type searches. So we look for example, long-lived SUSY particles that fly far in our detector, and then if we had one event that gives us something really strange in the calorimeter only type of analysis, then we would say that would be at least really interesting. So it depends really how well we know our backgrounds, in fact, as far as if we're able to build a tight enough signal region that we believe the background estimate, that it's really lower than one event, then perhaps, yes. But I would say, for the most part, we're looking for a few events in these signal regions, at least for something like a 3 sigma. And then, for a 5 sigma, you'd want, really a handful or combining several channels. Yeah, and in fact, just like the Higgs discovery, multiple channels is the key. You want these different decay modes so that you can say, oh, look, this is really a Higgs. This is not just some statistical fluctuation. This decayed to 4 leptons, and it decayed to diphoton, and at the same mass. So ideally, we'd like some sort of harmony between these different signatures, which is why for the SUSY searches, we have the all-hadronic and the 1 lepton channels that are really complementary to each other, and it's actually really nice. We're blinded separately. We have separate teams. We are orthogonal by design. And then we each unblind and say, oh, do you see something? We don't see anything, or vice versa. So it's a nice cross-check even within the experiment. And then plus you have CMS, so that helps too. But yeah. Yeah?
So standard model assumes that neutrinos are massless, but they're not. So how are the masses of neutrinos incorporated in the calculations and the Higgs mass and stuff?
Yeah, so that's certainly, these are really high energies compared to the neutrino mass. So for our day-to-day, it doesn't really matter. We can basically assume their masses compared to the interaction energy, right, and the energies of the constituents coming out. So yeah, I'm not sure if there's an example of a calculation where it would matter. Not for the LHC, I think, probably, yeah. Any other questions? Okay. Great. Thanks. Nobody asked about this over here. What?
Nobody asked about 752.
But I thought it should be a private.
Oh, I
Oh no, it's yeah. We can talk about it.
Yeah, so when's the next update?
Whenever the LHC turns on again, which is, I'll actually have the schedule in my talk tomorrow, but in case you don't make it to that, the plan is that we restart again in April, and so we just need to integrate enough data. So I'm guessing summer conferences, there'll probably be another update. So probably for ICHEP, which was actually in Chicago this year, so.
But not for Morion.
I think not for Morion, because we didn't get more data in the meantime.
Yeah. So you've already analyzed everything that you have so far for that?
For the most part, we have some SUSY searches that are coming out still, but yeah, for diphoton, it's all the data that we got, unfortunately. Yeah. The LHC didn't give us that much last year, so.
Yeah, oh, if you're going to do that, fine.
Yeah, I'm trying to do something. Yeah, this just got back on Tuesday, so here she wants to go to the museum.
Thank you.
What is the? I think you should go without.
That's fine. You're in?
Yeah.
Uh-huh.
Are you in for dinner?
Of course, you integrate time.
Yeah.
Yeah,
That's something
don't worry about it.
you have to stop and you have to change
Yeah, so
technology.
do you-
You
Yes.
have to change to new data.
Well,
Yeah.
What are the time scales?
Yeah, so,
Yeah, I think
I mean, I can tell you
The
that,
thing that impresses me is that I was a PhD student 25
it's
years
open
ago.
till 6, so I'm not going to get a reservation. But
So you're equally different on time scales that are comparable to
Yeah.
scales of
pay the students
That's right.
funds, grad student federal funds for teaching classes.
I'm mapping all the restaurants in town that have appropriate noise level and are baby.
I never heard that before, and I think a lot of us do that.
Squawks all the time.
yes, exactly, yeah.
It's tied into the,
So-
he was talking about the
so
program and like how it goes TAs and
Yeah.
research and blah, blah, blah.
Yeah, so we have another upgrade to the trigger electronics coming in like 2018, 2019.
So it's
But
not,
at that point, if we really see signs of supersymmetry,
I don't think that's
I think it's by the end of March.
Grad students.
There's one university that maybe it's just
We're
we're gonna have to go back to Santa Rosa. I mean, hopefully at that point, we're all hoping that we're gonna be like examining for success. That's right. In fact, I think so. And so, you know, me personally, I'm really interested in top work physics,
pretty well.
top Higgs. We can use the Higgs, for example, to look for new physics potentially. So you can look for top Higgs resonances, T-bar Higgs, anything like that. Maybe find something there that might be really interesting.
It's all because our
Right now it's
total,
statistics, yeah,
the
for
total
that
funding
still.
is only.
But eventually, you're right. I mean, there will just be, we'll keep integrating data, but the sort of the time it takes to get a factor of 2 of data will be longer and
yes,
longer
that was the
at
same
some
thing
point.
we always.
And so